So you can have like a long list of
Okay, if we're ready, I want to make the ready.
What do you do once you have tenure?
one day. Long dinner.
Okay, that's how you do it.
Our last speaker of the day is Naomi Saphra, who will take it from here.
Okay, yeah. So I'm going to be talking about compositionality and phase transitions in language models. And the first thing I'm going to talk about is just what is a phase transition? What do I mean by that in this case? So one example of this sort of like unpredictable sudden shift is grokking, a classic. It happens when you're in a low data setting. And the model memorizes the data, and then long after memorizing it, it generalizes to the same distribution that the training data was sampled from, but not the training data, since that's just memorization. Okay, another sort of a classic example now is the induction head phase transition. Happens during training in a language model. There is a particular moment when a circuit forms in multi-layer models where you have a lower head that searches for previous occurrences of a token, and then the next head will actually copy over the token after it. And this is essentially like a syntactic priming effect, but it's particularly useful for developing in-context learning, which is what you see measured over here, is a sudden model improvements on in-context learning in particular. Okay, and then the last phase transition I'm going to talk about is emergence, or just breakthroughs. Basically, a small-scale model is bad at something, and then suddenly you keep going larger and larger, and suddenly a large enough model is able to handle that particular task. We're going to talk about this later, in particularly the multiple choice question answering task, which is one example of something that is emergent in this way. There's a lot of controversy about these, and whether it's just a artifact of a metric that has some kind of thresholding effect. It seems that many of them are, but not all of them. And in particular, I would say not multiple choice question answering. So you can rely on that one as a case study often. All right, so these are all breakthroughs, either in scale or in the time dimension. But what makes a particular capability a breakthrough capability in this way? I'm going to argue that there are three facets of a task that make it have this property. There's compositionality, compositional structure, and reliance on compositional structure for solving the problem. And there is a competition between possible solutions that the model might produce for what it sees in the training data. And there's multimodality in the sense of clusters of performance when you look at a probability distribution or slight changes. So here multimodality means something along the lines of you know it or you don't, in the sense that you either have a very poor performing model or a very high performing model, depending on random seed. So I actually think that these are all sort of different ways of talking about the same property, actually, that causes this kind of breakthrough effect. And the first case study I'm going to talk about for breakthroughs and these properties is the phenomenon of sudden syntax acquisition in masked language models, which is this paper. So, okay, masked language models, they're not as popular these days, but modern BERT is bringing it all back. They are useful for certain things. Instead of predicting the next token in a sequence, you're predicting a masked out arbitrary token in a sequence. Pretty straightforward. Usually you use this to pre-train a model, you fine-tune it for other tasks. And the classic example is BERT, which is what we're going to use because it's not too big, but it's not so small either. It's made up of transformer heads, and they each compute some kind of attention distribution that reweights each token in the sequence, just like a autoregressive model would do. So there was an observation that a few different groups concurrently discovered, which is that some of these attention heads actually attend to specific syntactic relations. So if you were to say, like pick the subject relation, then you would find that there is a head that pretty consistently attends to the subject, we can call it the subject head here, of the target token. So if you've masked out wheres, you can see, okay, the subject token attends to the subject of that, the subject head attends to the subject of that token. So fairly straightforward. It shows up just naturally, and it is measured with unlabeled attachment score. So every time I talk about the degree of like internal syntax in a model, I'm going to be talking about UAS. If you care about it, then you care about it. Okay, so we know that mass language models have these specialized heads, and there's sort of an implicit assumption when you discover this kind of property that it must be instrumental in some related capability. You can just sort of make that intuition, right? So what do we actually have as evidence that the models are relying on these like internal syntactic structures for their actual capabilities, their grammatical reasoning capabilities? Well, there's the fact that they happen. It seems like if they happen, they're used for something, and that seems like a good thing they would be used for. And then there's the fact that, in fact, if you like ablate these heads, then it damages model performance more than if you ablate a random head that isn't one of these specialized heads. But just because we see it doesn't mean that it's actually a key part of how the model works. It could be some kind of side effect of training. And even if, that was very sudden. Okay, even if some of these heads seem to be more important for model performance than others, it could be that there's like a correlation between how entangled that particular head is with the rest of the model or something like that, rather than that specific property is the relevant property that the model is using. Okay, so we're going to actually look for some evidence for this, the importance of this property of syntactic attention structure. And we're going to do it by looking at the training dynamics of this property. So it turns out that this shows up extremely abruptly. This is absolutely one of these breakthrough behaviors that we're interested in. It's absolutely a phase change. And that it's accompanied by a very big drop in loss. And it's followed by a sudden increase in the ability of the model to handle complex grammatical examples. So we not only know that, so we've not only found one phase change, we've found two consecutive ones. So it seems that maybe just looking at this, that this is precipitating grammatical capabilities, so it's likely that the grammatical capabilities are relying on it. So I'm going to also mention, of course, that this is evidence that compositional structure is something that produces breakthrough phase changes, breakthroughs, whatever you want to say. So, okay. We want to get even stronger evidence, so we're going to actually suppress this property, and we're going to see what happens to the language model as a whole. The way we suppress it is by taking, say, the subject head and saying, okay, but what's the actual subject? And then just penalizing the maximum weight that's placed by any attention head on that actual subject. So that means that you can't really develop a specialized head for subjects, obviously. All right, so what happens if we suppress it? Okay, all of the red lines here are just normal training, and the cool colors are suppressed. All right, what happens is at smaller scales, actually we get better performance by suppressing the internal syntactic structure, which is very interesting, and we might want to talk about that later. But eventually, yes, you do actually get like much better performance by when you let the model learn this property, right? So and importantly, if you suppress it, you do not hit this like nice phase transition, and you don't get the grammatical capabilities of the model that is allowed to use this sort of strategy. But why are there two phase transitions? Okay, it's because there's some competing strategy that we've actually pushed the model towards by removing the option of representing syntax internally in this way. All right, then what does this bring us back to? It brings us back to the fact that breakthroughs are characterized by competition between multiple solutions. So if you remove one solution, the model finds another, and it has a different phase transition as a result. Okay, so, man, this is a little delayed. Okay, so now we're just going to go into another case study, which is on hierarchical generalization. So,
what you had shown,
oh yeah, let's stop for questions, yeah.
what you have just shown for BERT.
Yeah.
All those for causal transformers?
It's a little more complicated to talk about this internal syntactic structure in the case of causal transformers. It shows up to some degree. It's not clean in the same way, probably because causal transformers give you a sort of like starting, sort of like a head start on the idea that position is important, and specifically that like nearby tokens are important. So you can sort of get a little bit of that like chunking just from the actual like position that you get out of the causal masking itself, rather than having to sort of learn syntax almost to like almost at the same time as position is what I'd say. But it is there. But just like you don't see a thing that you would specifically call the like induction head phase transition in a masked language model, you don't see this kind of phase transition exactly in an autoregressive model. Yeah. Yeah?
So, like, you have this other solution that it's learning.
Yeah.
Loss, but you don't actually see that it's grammatical when you learn to.
Yeah, it's like, I mean, it's doing pretty well. The loss definitely goes down. It's not able to handle grammatically complex concepts like negative polarity indexing, like things that actually require you to think about hierarchical scope. The model doesn't pick up on that. But it's faster at learning long distance, sort of n-grams, stuff like that. It's kind of the things that you might sort of conjecture are what the model is learning faster in that situation are kind of the things the model is actually learning faster. It's like, not exactly, but to a reasonable degree. Yeah.
In your previous case study, have you looked into what the competing solution might be, or do you see anything emerge more successful?
Yeah. So like I said, it's actually not as clean. It's not like as clean as you might want it to be, but it is a case where you like the first thing that you learn is actually longer n-grams rather than shorter n-grams, right? Because you've prevented it from learning, small, phrases, because small phrases are often syntactically related. Yeah. So it sort of has a sudden like breakthrough of, oh, I can represent big n-grams. And we don't have like a really great mechanistic description of what's happening, but that's pretty much it's like appendix Q in our paper or something. We definitely did look at it, but yeah. Anyway, any other questions before we jump into a example that does involve autoregressive language models? Okay. So now we're going to talk about autoregressive language models. And we're specifically going to talk about hierarchical generalization behavior. So there's syntax is generally pretty hierarchical, so we have a lot of rules that are best described with trees rather than just like linear sequences of tokens, if everyone accepts this. And so we use these a few different tasks that sort of differentiate between these between different rules that you could learn, right? So in this example, in distribution, you're not exposed to anything that tells you whether to use this hierarchical rule, where you take the main auxiliary verb and front it, which is how you do question formation in English, versus a linear rule where you just take the first auxiliary verb you see and front that. So the in distribution examples are cases where this leads to the same output. So my unicorn does move the dogs that do weight. Does my unicorn move the dogs that do weight? That output could be produced by either of these rules. And then out of distribution, we're going to say what rule the model actually learned by checking whether it produces linear or hierarchical output on an input where those rules don't give the same output. So previously, people have shown that actually this kind of hierarchical generalization behavior, this syntactic rule, is learned in a grokking style long after the model has actually converged in distribution. So the model has been able to handle these ambiguous cases for a very long time before it starts to specifically favor the hierarchical generalization rule that uses the tree structure. So okay, that's a sort of a breakthrough thing. We've talked about grokking as a breakthrough phenomenon, and this is a case that people would call compositional. So here's another for our list, right? And the thing that allows a model to learn the hierarchical rules specifically in these ambiguous training settings is when it's exposed to center embeddings in its general language modeling practice. So these center embeddings don't show up in the actual examples of question formation, because that would sort of give away what the real rule is, but the model still gets to sort of model center embedding sentences. So the reason why center embeddings are so important, and linguists generally agree that they're important for learning grammar, is because English, for instance, mostly is branching rightward. So if there's no center embeddings and each head is getting just your one relative clause, it's going to keep scoping forward, and you can basically treat it as though it is just a line or an n-gram model. You don't need to use hierarchical structure in that situation. So that's why center embeddings are so key for creating a bias towards hierarchical structure. And we definitely do see that. So here what we're looking at is if you have the data set that has both center embedding and right branching, non-center embedding examples as language modeling examples. Question formation is still only ambiguous examples. You see that that it is generally pretty decent at learning this generalization behavior, becoming hierarchical. If you remove all examples of language modeling, then it is very bad at that. And these are across random seeds, by the way. We're training a bunch of different language models. That's where the distribution comes from. If you only introduce center embeddings and you give absolutely no exclusively right branching sequences, as in the examples for language modeling, then it always basically learns to hierarchically generalize. And if you give it no center embeddings, then it's pretty bad at learning that. Although notably not actually following the linear rule consistently, which we can talk about later if I have time. I have a little if I have time thing at the end. All right, so in general, it seems that we've seen that complex training data teaches complex rules in the sense that training data that requires hierarchical modeling teaches hierarchical generalization. Yeah?
Can you explain that chart, please? Like, what is UD Gen Ac?
Yeah, sure. Gen Ac is generalization accuracy on this out of distribution set, which we're going to, which the correct rule in English is the hierarchical rule. So if you're following the hierarchical rule, then you will know how to form a question on 100% of the out of distribution set. And if you consistently follow a linear rule, then you will do it on 0%. And if you're doing some kind of weird mix or you don't know what you're doing, you're going to be somewhere in between.
And so do the thicknesses of those vertical columns mean something?
That's just the vertical column.
Yeah.
Oh yeah, this is the size of the data set that it's being trained on. Since we remove some of the data when we say, okay, we don't want any of the right branching data, we don't want any of the center embedding data, we end up removing a little bit of data just so that you can sort of look at it and say, okay, some of this might be just due to the amount of data available.
Okay.
Yeah. All right. So, yeah.
I guess just, I'm a little confused with how you're using the term compositional.
Yeah.
Isn't the grokking example non-compositional?
Right. So, so I would say the grokking example is like a bit of a weird one because it's like you're choosing between a systematic rule, which I would argue is compositional in a sense. And so what I would say is, in this case, compositional structure is important because what you're selecting is the latent space that you're doing your compositional reasoning within.
How about like emergence of copying compositional? I guess I'm just trying to find a counterexample that's not compositional.
Yeah, I mean, I think that the unfortunate thing about compositionality is that it's quite easy to argue that anything is compositional if you want to, but yeah.
Isn't that the main claim you're making? Like, how would someone falsify?
Yeah, I would say, okay, so the main thing is that compositionality is really that it's not enough to say this is compositional. But that, in fact, what you're talking about is whether you're reasoning within some latent space that's being composed to produce the output, right? And so the fact that you can choose between multiple latent spaces to operate within is the thing that creates this breakthrough effect. Yeah? So I would say that the in-distribution generalization in grokking is a type of compositionality in that it can in that it is extrapolating in some latent space to handle examples that aren't in the training data set. But it's not exactly the kind of breakthrough that we're particularly interested in because it's only created by the low resource setting that makes memorization a viable strategy in the first place. Because you're not really leveling up that latent space to be something that's more complex than just addition in distribution.
I mean, not to belabor the point, but it does feel a little bit tautological.
Yeah.
Is something that exhibits breakthrough.
No, that's fair. I'm not trying to define compositional tasks as any task that exhibits a breakthrough. I do agree that the grokking case is not sort of it's not the kind of compositionality that people are really usually referring to when they say compositional, because usually people mean you're operating in a more interesting latent space than just one that works in distribution in this way, and instead that you'd be operating in some kind of latent space that allows you to make out of distribution claims. But when the training set is that small, it's now you've created, now in distribution becomes out of distribution because you have so few examples. So it's like then you're sort of choosing between, like this memorization and what is sort of technically compositional, but is not like compositional in any way that people are interested in when they talk about compositionality.
Sorry.
Yeah.
Just in view of all this, can you step back and just
Yeah.
say in simple words, what do you mean by composition?
Yeah, no, I mean, so what I'm saying is, in general, I would say that like a task is compositional if you are extrapolating out of distribution using some kind of latent space that like makes it clear like how to extrapolate in some sense. So I would say like the one thing that I would never really describe as compositional is like memorization. But when people actually talk about compositionality, they're talking about many different things. I recommend Duca Hupkis's Compositionality Decomposed on the topic of like all of the different things that people often are referring to in practice when they talk about compositionality. But I would say the unifying property is that they are all describing how a model will handle out of distribution data. And the thing that people are interested in really, and the thing that makes it compositional, is that you're literally composing, like if you think of a compositional function, that there's literally a like latent space, which is to say the inner function, in which you can, like from which you can extrapolate at the output by like reasoning within that space. That's like the connection that I would generally make to like the way that, to the literal like definition of what it means to compose a function, is that. I think there are, the actual like question of it is like pretty significant for like, like people talk about what counts as compositional a lot. And
sorry, is it fair to say that the definition
yeah.
you're using for compositional is synonymous with generalization?
I would say that that generalization, yeah, it's not unfair to say that it's basically like synonymous with generalization. And I think that the fact that most of the time when people are talking about compositionality, that they're talking about what a model does when exposed to out of distribution data makes that pretty clear. Like I said, I do think that the case of like grokking, where in distribution becomes out of distribution, is kind of like interesting in that it illustrates that even the things that we wouldn't describe as compositional because they're not like interesting as compositional spaces is kind of like yeah.
For the grokking example, like if I think of this algorithm that's talked about in that Neil Nanda paper, where it like sort of maps the input to the circle and does sort of a little bit.
Funny enough, that's not the correct algorithm. There's a recent paper on it. But yeah, go on.
But like, is the fact that I'm doing like multiple operations there, one of which is mapping to like a different space, like, is that what you have in mind with this, with calling grokking compositional?
Yeah, basically, like that there is an abstract space in which like addition occurs. And it doesn't have to be like this this sort of space that they conjecture or that they describe. It's not. It doesn't have to be that kind of space. Any space where you can do addition on unseen examples is, in that sense, compositional because like you're extrapolating in some representation of the numbers themselves, right? So. I do want to actually go on from here, but I would say that all of these things distinguish like composite functions, and that's the thing that makes these like bimodal, that makes everything happen, I would say, because either you are operating in the right latent space that you've learned or you're not, in that sense. You could learn a different latent space. In this case, obviously, you do. The linear rule is compositional in its own sense. It's just not hierarchical. because you can still extrapolate in the space that assumes like a linear sequence. Okay, I do want to move on from that, because I think when I'm saying compositional, I'm not saying, oh, if you are compositional, then you have this property. I would say that compositional structure is the thing that differentiates what can be a breakthrough, like a breakthrough sort of phenomenon, because there are multiple latent spaces in which you could be reasoning. And therefore, it has to assume that there's latent space that you can reason within. So, all right. Right. So what happens then if you mix these? Different? Okay, I'm gonna go back for a second. The complex training data teaches the more complex rule in the sense of the hierarchical training data teaches a hierarchical rule, right? But then what actually happens if you mix easy training data in this sense with hard training data is that it doesn't actually lead to consistent out of distribution behavior really at all. So, so this is specifically looking at like the right branching examples in the out of distribution data set. So this is where you don't already have a center embedding that you're looking at. Does the center embedding allow you to generalize hierarchically on those examples? So the more center embeddings you have in training, generally the better the performance of the model is going to be. But there's a lot of like variation that you can see over here, right? So so the sort of the thing that I would want to highlight is actually like that these mixes create competition, and specifically it's competition that you can see in the training dynamics of a model that's being trained on a mix of like easier and harder data. So, all right, we're going to measure the stability of the training curve with total variation. So here's just an example of two different training curves in terms of their generalization accuracy out of distribution. One of them just shoots up immediately, it learns hierarchical generalization, it stays there. The other is oscillating a lot. And so total variation is high if you're oscillating a lot, it's low if you are stable. Okay, so what happens when you look at this for different data mixes is that you can end up with a lot of sort of oscillation, which is everything that's more on the right side of any of these plots. And you end up with more oscillation regardless of which of these mixes you're in. You can still end up with like a lot of oscillation. Now, if you are mostly linear or not linear at all in terms of the training data, if it's fairly homogeneous in this sense, then most of the models end up pretty stable one way or another, either in one rule or the other rule. And then in between, you can see more and more of these models end up more and more to the right. They're less and less likely to stabilize completely. So in general, it turns out that if you commit to one of these rules, linear or hierarchical generalization does not matter, then it's associated with the stability of the curve. And if you don't, you keep on oscillating, trying to decide between rules. Everything that's sort of like on this end of each of these plots, you can see is stable, and is very, very close to either 0 or 1, is very close to a systematic rule. So this is an example of how these like breakthrough capabilities are actually multimodal. They don't necessarily look multimodal until you control for the level of stability, which expresses the competition itself. So if the competition resolves, you end up with multimodal sort of distributions across random seeds. All right, so the third thing we're going to talk to is this like case of emergence, right, in general across scale. So this is a case where it turns out that it's a little both simpler and more complicated than like one plot with a big breakthrough would suggest. And I'm going to be talking about specifically length generalization, and specifically this setup that makes it a little easier to do length generalization, where you train on just 30 characters, you test on 40. It makes it a little easier to do length generalization if you give hints about what the index of each point in the of each digit is, and also you let it produce the output in reverse order. So, okay, this is a type of compositionality that's generally referred to as productivity. So it's a question of, are you behaving productively or not in terms of being able to like extrapolate the algorithm you're using to longer sequences. Okay, so yeah, you can look at the scale curves, and you do see like a big jump, emergence on this one seed that I am showing you right now. So, okay, there's an example of like where like a particular type of compositional structure allows you to have this kind of jump where you pick up on the right kind of latent structure. And so, yeah, you get emergence. But not necessarily. And it turns out if you look at other seeds, they look very, very linear in their scaling laws, yeah?
What's the positional encoding scheme for these models?
Rope.
Okay.
Yeah. So, okay. These are generally claims when people say this is emergent. They're generally making claims about scalar values, usually a single seed. Sometimes they average like 3 seeds if they're really like if they really have the resources, but usually not. Usually like they're literally training one model at each scale, right? And so when you're doing that, and then you suddenly say, okay, well this is like a breakthrough capability. This is emergent. You're not necessarily getting the full picture, right? So how is it that you can have so much variation across different seeds? It's because of the bimodal distribution, again. So either, so in the purple side, this breakthrough side, you're sampling from over here, and then suddenly you're sampling from your like successful component of the distribution. Whereas with the linear improvement, you're sampling just from like a lower point in that component and then a higher point in that component. So, so you can see that these are like cases where you might not know the actual point where the model has the capacity to represent something, and where your claims about specific scaling trends are going to potentially be really dependent on random variation. So there you have your multimodality effect again. Okay, so so then the individual scaling laws that you produce are generally going to be sampled one seed at a time. So they end up probably looking something like the mode. So the mode you can see is extremely emergent. It's a huge jump over here, right? That's like if you measure the mode of the distribution across random seeds, there's a big jump. But if you actually look at the mean across many seeds, it ends up looking like smoother. Generally. And the reason why is because the actual underlying distribution is changing much more gradually than any one seed might suggest. So you can see that there is a like slow change in the probability of a success, as you would measure by looking over here. And there's a slow change in the the average case for a successful model that you would see when you look at this component, and those are much more gradual than you would get from looking at like a single seed, right? As long as we have an actual minimum capacity, which here is much lower than you would think the minimum capacity is just based on where the emergence happens. it's like at this scale that you actually start having some successful runs. Okay, so that mode being super discontinuous, as we've seen, is actually just expressing a gradual change in the probability of success, not a sudden change in the capacity of the model at that scale. And then we can see a similar kind of effect of random variation being really key, or like random variation being making it really clear that there's a bimodal distribution underlying emergence. When we look at multiple choice, which I mentioned is a pretty widely accepted at this point actual emergent capability. So the issue here for most models is that the model literally has to compose the format with its like knowledge base that it's using. So that's where the actual latent reasoning has to happen, is in handling the multiple choice format, and either you pick up on that or you don't. So if you fine tune at a smaller scale, the model will pick up on it faster because you can learn that format at smaller scales. It's just not necessarily going to be worth learning in some sense from the entire training distribution at that scale. And if you take a decently sized language model, not huge, but it's fine, right? And specifically one that is not capable of handling multiple choice questions before you continue pre-training with a mix of a little bit more multiple choice. You can see that mixing in a little bit of multiple choice questions when you continue pre-training the model after reinitializing the last layer. So you reinitialize the last layer, right? And then and that gives you the random variation back. And then when you train the entire model just normally, right, you end up with these bimodal distributions again, and they only emerge specifically at certain data distributions where it's sort of precarious whether it's worth, let's say, representing the multiple choice format or not. All right. And then it's also pretty visible in terms of scale. So you can take that same distribution of data that you used on a 500 million model and you hand it to a 1.5 billion model, and it's always enough for the 1.5 billion model to be it's worth learning this format. Okay, so whoops. So that's another case where we can see multimodality. Okay, any questions at this point? What are we? Oh, okay. I have a whole thing about U-shaped scaling after this, but you'll have to ask me about it after because it's almost 5. Does anyone have questions now? Yeah.
Me?
Yeah.
Yeah, thanks for the talk so far, I guess. I always think of emergence and these breakthroughs as kind of a proof of existence.
Yeah.
So is what you're arguing that it should be a for all rather than a there exists?
I am saying that often people are assuming there is a capacity at that point where it breaks through, which I don't think is correct. But also, it's fair to say that there's at least one possible model that would be produced at that point. It's also, I guess, fair to say that there's a possibility of initializing into a good model at a much smaller scale, maybe something like that, even if it's not learnable. But that's an extremely tiny probability, right? So for the point where we actually care about whether a model can learn something, we might see something show up at a scale that is long after the model has become capable of expressing that. And also, like, I think that there's that it's worth thinking about whether improvements in performance, like in the average case performance, for instance, come from improvements in the probability of a successful model or the performance of like the average successful model, which are two different things.
I see.
Yeah.
I'm sorry, like, let me know if I just missed this, but my sense from all of this is we have multiple picture of like the kinds of capabilities that might be breakthrough. But like, why do we have any sense of like why spiking like that, like breakthrough as a form of learning is like a viable way of learning compared to something more like gradual? Like, is there any incentive for like why a system that learns would be incentivized to do things like that, where it spikes, versus like gradual learning throughout?
Yeah, I think it's that the key is really this is actually this random variation being being a factor, because even if you look at models where a population of models where like they all end up learning to generalize, they can cluster in terms of their training dynamics, where there are like specific points where the model ends up sort of picking up on the key concept, and it can be very clustered. So I think in that sense, there's maybe like the probability of discovering sort of a useful shortcut. Like there's something that piggybacks on something you've already learned, but in order to make that jump, you need to sort of have like a lucky batch, or you need to be sort of initializing in the right position, this kind of thing. Yeah?
I was wondering if you've tried to disentangle those, like to keep the training data order fixed and only change the initialization and vice versa to see.
Yeah, and our conclusions are like a little messy from that. We do see that there are certain things that are very affected by initialization and not really affected by data order. So if you just change the data order, for instance, when you're fine-tuning, you only end up with one cluster, like in a single basin, and in the sense that everything is like linearly connected with no barriers in that basin, and all of the models have like a similar out of distribution sort of behavior strategy. But you end up with serious clustering if you actually do the reinitialization. So I would say that we have some evidence at this point that random initializations are very important, and that data order can be important, especially depending on like the stability of the initialization. Yeah. Yeah.
Okay. I just want to make sure that I understood some stuff that you said first before I get to my question.
Yeah.
So this sort of multimodality is relatively early on in training. The model learns two possible solutions to explain some phenomenon, and it's sort of ambiguous between those two until it commits to one, and then you start to see a stark improvement in performance when it commits to one of these solutions. And that might be because it just decides to do one, and both could have been equally as good, or sometimes one is significantly, it makes a lot more sense than the other. Is that?
Yeah, like I would say that you would maybe want to look at it in terms of like compression or efficiency in some sense. Like I think there are a lot of ways of looking at why one solution might be preferred over another once it is discovered, or like in a sort of like when both are sort of in open competition, like when you see these oscillating training dynamics.
Yes. Yeah. And because of that, we see this sort of like linear increase in probability before we start seeing this this sort of emergent increase in how it produces an output that matches the correct output, because you're mainly evaluating on the production as opposed to this probability. And
yeah,
it sort of reminds me something about Michael Frank's talk earlier, where he was discussing about how we see in humans and in language models, we see comprehension before production, Do you think that's sort of related in that way if we think about it in that sort of cognitive science aspect?
Right. I think that I don't want to I think that there are a lot of concepts from cognitive science that are useful for reasoning about these things, but ultimately a language model is not a human and doesn't learn language in the way that a human learns language. And I think that these jumps make it fairly clear because you don't only see so you don't only see like scaling effects in one direction kind of thing, right? You can also see U-shaped curve, and those U-shaped curves aren't necessarily the same U-shaped curves a human would exhibit, for instance. I think that the parallel between like competency or between comprehension and production is like a potentially useful one, for instance, in that first example that I gave where there's an internal structure that's learned and then it precipitates grammatical capabilities. But I wouldn't compare it to any actual human like language development.
Okay.
Yeah. I don't know if that answers the question. I mean, like, I think that these are like useful concepts, but I think that you can overcommit to parallel to like anthropomorphizing, especially in the case of learning, which is so different for these models than it is for a human.
Yeah, I don't know if it's necessarily anthropomorphizing. It's just saying there might be a similar pattern of the observed behavior, but yeah.
Yeah. No, I mean, I think it's a useful concept to import, like I said. Yeah. Yeah.
Yeah, so my question is perhaps slightly related. So I was wondering what your thoughts are on the developmental trajectory of competition between solutions. Specifically, I think the received view in the graphing literature, like from the model validation paper, for example, is that you have some kind of heuristic or memorization phase that's suboptimal, and then you have circuit formation of a general solution, and you get a removal of the initial shortcut solution to let the general circuit be expressed. I see these are that's characterization, but
sure.
Maybe I'll just finish and then you can tell me.
Yeah.
So I was just wondering whether that's what you think is going on here, where like you have competition initially and then the suppressed solution just gets removed, or you just have a winning solution and the suppressed solution is not removed, but it just doesn't have as much of an effect on the logics at the output than the...
Yeah, I think both can happen actually. So, another random variation paper that we did, where the first author is Michael Hu, we found these like clusters that I mentioned in the training dynamics instead of in the actual like performance, and this is specifically for the like modular arithmetic sort of grokking case, right? So we did find that if you use the exact same settings, there are certain initializations that lead directly to generalization. So you can discover that. And then there are also certain initializations that take so long to grok that, that they are generally treated as like failed runs in the actual grokking literature. If you keep going, they actually do eventually grok because eventually you get, let's say, a lucky batch or something, right? But I do think that that it seems to be that you have these stages in which there's actual competition between, like you said, the generalization circuit and the memorization circuit. And as long as you have like weight decay, like as long as you have like actual regularization, that eventually you favor that generalization circuit. But I think it's harder to make a broad claim about like what drives competition in one direction or another, because for a lot of the training, it often isn't clear that there is like a winning side.
Right. So my question is not so much what drives the competition as much as when a solution gets favored, what does that mean? Does that mean the other solution is removed? Or does that mean it's still there, like there is a circuit in there that has an effect on logics, but it's no longer affecting the outputs? Which,
Okay, now I understand a little better. Yeah, we have another paper on random variation where we did find that if you don't have enough regularization, sometimes you end up retaining a vestigial circuit that doesn't have any effect in distribution, but then has but then it ends up sort of dominating out of distribution judgments. So it's like you can pass through a strategy early in training that ends up shaping out of distribution behavior even later on and isn't pruned out, but only if you're insufficiently regularized. Otherwise, you prune it out.
Thanks.
Okay. All right. This is a slide that starts an entire side thing, and you can talk to me about U-shaped curves after this if you're really interested in U-shaped curves. Well, okay. I will plug it back in just so I can show you, just so I can quickly speed run through this. Okay. No, you missed the animations. I'm sorry. We had too many questions. There's no animations. This is one of them. This is a sort of one of them. Yeah. And then this is the weirdest one of them, where we found a synthetic task that has a very clear U-shaped curve for specific ways of scaling. Okay.